What the heck?
Tagon.
Hello! So, you're a little close to me. Hang on. Ooh. Alright, so today begins our first lesson in real analysis that I've been saying I'm going to be doing for a while now, but we're finally going to get started. So, we're going to be reviewing a couple of topics before we sort of delve into the real meat of the subject. And the topics that we will be reviewing are as follows. We will be reviewing sets. We will be showing that irrational numbers exist. We will be reviewing properties of sets, like the ones you're familiar with, like union and intersection and various other aspects. We will be reviewing functions in the context of real analysis, so not necessarily thinking of like a curve, but something that in a very basic sense just assigns one element of some set to the element of another set. And things like injection, surjection, bijection, the triangle inequality, and then we will be going over methods of proof, which include things like induction, contradiction, and direct proof. So that will be our video for today, potentially split up into multiple videos if it takes a long time, but that's essentially the introduction, and then after that we will be starting to get into talking about the real numbers as they currently are understood. So, if there are no questions from the audience, then let's get started. So, welcome one, and welcome all to my series on real analysis. So we'll be covering more or less the entirety of the subject as it currently stands over the course of the coming months, with full intention of continuing on through complex analysis and potentially functional analysis and measure theory, if I'm well versed in those subjects by the, enough by the time that we get to covering the topic. But this will be a very, very long project of mine that I want to embark on, which will be covering the subject of real analysis in its glory, and fully understanding the foundations and justification, the rigorous justification of the subject of calculus and the topics of limits, derivatives, and integrals, and things like that. And so this will really be the quintessential collection of lessons on this that isn't a formal lecture or something that you have to pay for. So let's get right into the meat of the topic, so to speak, by reviewing some of the concepts that we're going to be using throughout the entirety of this I would call it a class almost. So let's erase my stylized title there. And let's talk about what we're going to be reviewing. So first is going to be sets, the idea of a set. So a set of things is notationally written as pair of curly brackets, sort of like parentheses, with things listed in a comma-separated list contained inside those brackets. So it's just a collection of objects. And each object inside of a set is known as an element of that set. So you could think of these as being different definitions, right? So a set is a collection of things, and those things are called elements. It really could be anything. A, B, and C could just be the capital letters A, B, and C. They could represent numbers. They could represent other sets. It's anything at all that you can put inside a box, and you can, of course, put boxes inside of other boxes. So sets may contain sets at certain points, and we'll be using sets that do contain other sets to prove very fantastic results about real numbers later down the line. Get it? And so this is just a review of the terminology. Let's take a quick look at certain types of sets. So I just showed you a set that was finite, right? It has a collection of only a collection of three objects. But in principle, we could have as large of a set as we want, right? I could have the set from 1 to ... all the way up to n, which of course can be as big as we want because I can make n as big as I want, where of course these are all the whole numbers from 1 to n. But because I can make n as big as I want, you could almost talk about, and we will talk about, the set of all of those numbers as a specific set, an infinitely large set, in fact. So this is the set of all the natural numbers, 1, 2, 3, all the way up to infinity. So it's an infinitely large set, and so in some in a certain rigorous sense, right, this is a larger set than any of the finite sets of integers, right? It has to be a larger set because it simply always contains more than any finite set. And in some sense that we will develop over the course of this is the smallest of the infinite sets, right? We can have other sets that have the same amount of things in them. For example, and we'll justify this later, if we have the set of all the even numbers, right, 2, 4, 6, 8, right, then 1 can be associated with 2, 2 can be associated with 4, 3 with 6, 4 with 8, etc. And so in some sense, because you never run out of elements of either set, they're sort of the same size. And so even though they contain different elements, in fact, one might be able to even say this contains less elements than that because none of the odd numbers are there, we can still associate one number in this set with one number in that set. In some sense, they're the same size, even though they're both infinite. And we'll get to talking about, different sizes of infinity, which is sort of a crazy concept if you haven't encountered it yet. But yeah, so we have our most basic infinite set, which is simply the set of all of the numbers that we're used to, the positive whole numbers. I will be using this notation to mean strictly 1 to infinity. If we do this notation with a little 0 there, then that means we are including 0. Also, let's be clear, sets do not necessarily have to be ordered collections of things. There's no necessary sense of order, but whenever I mention the natural numbers, I am talking about the set of all the integers that is in this particular order, from 1 to infinity, in increasing order. And if I ever use these particular symbols, I'm talking about the sets as they appear in order. This may also sometimes be written as positive integers, right, where z represents the integers, so let's be clear about that. Z is the set of all positive and negative integers. So coming from the left as well, we have -3, -2, -1, 0, 1, 2, 3. You could call it a bi-infinite list or a bi-directionally infinite or stuff like that. I think there are phrases that essentially speak of things that are infinite in both directions, whereas these are infinite in a single direction. And so these are pretty natural sets that we would want to consider. Of course, z minus would simply be all of the negative integers. But I'll probably never use this really. I'll just use this to mean the positive integers, this to mean the positive integers and 0, and this to mean all the integers. That will be the general trend. If I do n minus, then that means I'm talking about the negative integers. So there's another aspect of numbers that we can do, which is divide them together, right? All of the things, to get from here to here to here, we sort of have to investigate multiplication, addition, and subtraction. But there's division that we haven't considered yet, because if I were to take 3 divided by 2, I wouldn't get a whole number. And so the answer to 3 divided by 2 appears nowhere in any of these sets. And so what we have to do is define a new set of numbers that we will call Q for quotient, which will be the set, and this is now called set builder notation, which is opposed to listing the elements of the set. I'm going to give you a general rule that describes each of the elements of the set. So this is going to be the set of all A divided by B, such that A and B are integers, so they're contained in the set Z, and B is not 0. So those are the rules, right? A divided by B, where A and B are integers and B is not 0. So A and B are any integers you want, except that B is not a non-zero integer. And instead of using this symbol for and, we could also use this symbol for and. I believe that's the and symbol. It's either and then or, which is the flip of them. I think that's the and symbol. So we can say this and that. Right? That's the rule for this. And so this contains all those numbers that we're pretty familiar with that are fractions, right? 171 over 39. This can be simplified, but that's sort of irrelevant. 72 over 73. 1/2, right? -3 over 1006, right? All of these numbers that we think of as just a whole number divided by another whole number, they're all contained in this set. And we'll find out some surprising facts about this set as we go on. And it may be tempting to think that this is all the numbers, right? Because it's not too hard to see that if we were to take any two arbitrary fractions, a over b and c over d, it's not too hard to see that the average of these two fractions, which would also be a rational number, has to appear between them, right? So we can quite easily calculate that. That's going to be AD plus BC divided by 2BD. That's going to be the average of C and D. I'm sorry, that's going to be the average of A over B and C over D, because the average of two numbers lies strictly between them if they're not equal to each other. Then this must be between these two numbers. But it's also an integer divided by an integer, which makes this also a rational number. So we found a rational number that is strictly between two arbitrary rational numbers. We can now consider this to be our C over D and find another rational number between those two and between those two and between any two we pick that aren't equal to each other, right? So this suggests that no matter what two rational numbers you pick, no matter how close they are to each other, you can always find another between them, which leads to the conclusion that there are infinitely many rational numbers between any two non-equal rational numbers. And so that may lead you to believe that the entire number line, which we will be considering, which goes, of course, from negative infinity to positive infinity, where 0 is in some sense in the middle, and there's 1 and 2, and all of the fractions between them, right? You may think that consists of all the numbers, right? This is every single number that appears on the number line. And we're about to see that this is simply not the case. Let's just quickly cover some more notation before we move on to showing that not all of the numbers are rational. By the way, all of these sets are contained in the rational numbers because they represent all the numbers whose denominators are 1, right? So where b is 1, we end up with one of these sets, right? If we make no restrictions on a and we just say that b is 1, then we get the integers, right? Pretty simple. So let's just cover some more notation, and then we're going to demonstrate that not all the numbers are rational, simply by showing that a single number which is not rational does in fact exist. Real quick, if we have a set A, and this could be a collection of anything, it doesn't really matter, it's a collection of stuff, right? If A is an element, little a is an element of big A, then we write that A is contained in A, like so, like that. A little 3, it almost looks like the euro symbol. If little a is not in big A, if not, then we write that A is not an element of A, like so. Quite simple. Now that we've talked about the really familiar types of sets, we're going to prove that not all of the numbers that we will be studying are going to be rational numbers. And then we will talk about a few more properties of sets. I just want to show that this exists because we mentioned natural numbers and integers and fractions and whatnot, so let's just simply talk about something that definitely is not rational, and that would be, of course, the square root of 2. So this is the number that when I multiply it by itself, I get 2. And you can do numerical calculations of this and see that it's around 1.414. Probably convince yourself that no matter how many steps you take, you're always going to have more digits to find. You do not know, of course, that it will repeat or not, and so this is what we're going to have to prove. We cannot check every single fraction. We can, we can limit our search to things that are definitely close to square root of 2 as fractions, but I'm going to prove to you that there are no fractions that are equal to the square root of 2. And this is a pretty basic proof. It's one that's been shown since time immemorial. It's literally thousands of years old, right up there with the proof of infinitely many primes. It's quite simple. In fact, Numberphile has done it before, but I will present it here just to remind you. So what we're going to do is we're going to sort of do an odd thing. We're going to assume that we can actually write the square root of 2 as a fraction. So a and b are integers. Of course, they either have to both be positive or both be negative because the square root of 2 is positive. We know that b can't be 0 because the square root of 2 is something that we can, at least manipulate. We don't want b to be 0 because then it wouldn't be well defined. So let's just do some algebraic manipulations of this and see if we can derive anything that can't possibly be the case. And then we'll talk more about the general idea of what we're doing here at the end of the video. We can either assume that a over b is in simplest form, or we don't have to. Either way will lead to a problem, but let's just assume that it is in simplest form. That will sort of motivate the end of the proof. So what we're going to do is we're going to square both sides. We're going to raise both sides of this to the power of 2, and that's going to give us 2 is equal to a squared divided by b squared. Now we said, again, that a over b is in simplest form. That means that at least one of a or b must be an odd number. Because if they were both even, then that means I could cancel a factor of 2 out of a and a factor of 2 out of b, and we would have a simpler fraction, which is in contradiction to our assumption that it is in simplest form. So let's just manipulate this a little more. This implies that 2 times b squared is equal to a squared by just multiplying b squared over. But what does that tell us? That tells us that a squared is some integer times 2, which means that a squared is even. Right? Therefore, a squared is even. But what we can investigate now is what happens when we square any even number, and what happens when we square any odd number. Even and odd numbers are of this form, right? Even numbers are 2 times an integer, and odd numbers are an even number plus 1. And when we distribute this power of 2 into here, we get 4 times n squared, which can be rewritten as 2 times the quantity 2n squared, which is precisely an even number, right? Because it's 2 times an integer, right? So any even integer squared yields another even integer. Done. But we don't know if that's the case with odd numbers, so let's check it out. So we're going to FOIL this out like we would normally, like we learned in algebra. We get 4n squared plus 4n plus 1, which is precisely 2 times the quantity 2n squared plus 2n, all plus 1, which is an odd number, right? It's 2 times an integer plus 1, which is odd. That tells us that if a square number is even, that its square root must also be even. Or if a square number is odd, then its square root must also be odd. There is no in between. So if a squared is even, we therefore have that a is even. So to avoid any issues with our assumption that a over b is in simplest form, it must be the case that b is odd. Because if b were even, we would be able to cancel a factor of 2 out of both of them. But let's just see what happens. So a is even. So we know that we can write a as 2 times some other integer that we'll call c. because it is even, right? So that tells us that a squared is equal to the quantity 2c squared, which is of course equal to 2b squared, right? We're just replacing a squared with 2 times an integer because we know that squared because we know that a is 2 times an integer, and we're setting that equal to the thing we had before. Foiling, not foiling, but distributing the power there, we get 4c squared is equal to 2b squared, and we can divide both sides by 2, so we will get the conclusion that 2c squared is equal to b squared, which tells us that b squared is even because it is 2 times an integer. And by the same logic, that tells us that b is even, which is what we will come to know as a contradiction, right? We assumed that our fraction was in simplest form, and we proved that it can't be in simplest form despite that assumption, because both the numerator and denominator are even, which means we can cancel a factor of 2. And you may think, okay, well, Sam, Mr. Hectagon, we can just cancel that factor of 2, and then we'll have a simplest fraction. But once we cancel that factor of 2, there's nothing stopping us from doing it again, right? We can say that a is 2c and b is 2d, then we cancel the factors and we get c over d is equal to the square root of 2, but then there's nothing about the symbols c and d that stop us from doing this exact same argument and deriving again that we can cancel out a factor of 2. So we could have done one of two things. We could have done what we did, which is assume that it was in simplest form and show that it isn't. Or we could just assume that it's a fraction and that we can cancel infinitely many factors of 2 from the numerator and denominator, which is not the case for any integers a and b, right? No integers have an infinite number of factors of 2, because then they would be infinitely large. And so no matter which path you took, whether you assumed this was simplest form or not, you will get to something that does not make any sense from the assumption that the square root of 2 is a fraction, and therefore the square root of 2 is not a fraction for any a and b that are integers, which means the square root of 2 is not an element of the rational numbers, right? That confounded the ancient Greeks, right, and the Pythagoreans and people like that who just were so fixated on the idea that rational numbers were the only true numbers in the world and that there was no such thing as a number that couldn't be expressed as a ratio of 2 integers. In various other studies of math, we know that we can arbitrarily approximate the square root of 2 with rational numbers. We could do it with its decimal expansion, which isn't very efficient, but you moreover would want to use the continued fraction expansion. We won't be talking about continued fractions here, but there are ways to get as close to the square root of 2 using fractions as you want, but you can never get there, or else this proof would somehow be invalid, right? But there's no contradiction in the proof in the sense that the proof is bad. There's a contradiction with the assumption that the square root of 2 is rational, and therefore it can't be, right? Now, we haven't necessarily proven that the square root of 2 can actually be written as something to do with rational numbers, and that's all those things that I've just said would have to be proven. But for now, we just know that the rational numbers themselves are not the only numbers, because we've just shown that whatever number we have to square to get 2 cannot be expressed as a fraction. So that's done, and so we know that, at the very least, all we can say there is that not every number is rational. That's the best that we can say. And it's going to come down to expanding our knowledge of numbers to the real numbers, which we will eventually construct from the rational numbers that we will need to actually study, right? The real numbers are the things we're going to need to study. So now that we've covered that topic, let's just cover a couple more properties of sets. So sets have different operations that you can do on them. We have the union of two sets. The union of two sets, expressed like so. So the union of two sets A and B is written as A union B. And this is the collection of everything that is in A or B. So, for example, everything in A or B. We can actually define it using set notation, right? That would be the way to do it. So it's the set of all x's such that x is in A, or, which is this V symbol, x is in B. So if it is in A or B, we're putting it in this set. Then the intersection of A and B, given by this upside down U symbol, is everything in A and B. So it has to appear in both sets to be included in the intersection of the two sets. By definition, using set notation, this is simply all elements x such that x is in A and x is in B. So this is particularly the things that appear in both sets. To give a concrete example, let's say that A is the set 1, 2, and 3. So the set of the numbers 1, 2, and 3, and we'll define B to be equal to the set 2, 3, and 4. Then quite clearly the union of these sets is everything that appears in either set. This is going to be everything in here combined with everything in here. If something appears more than once, we don't list it more than once. It just appears in both sets, and so we consider it as part of the thing. The union of these sets is going to be the list of everything that's in A, 1, 2, and 3, and then everything without redundancies that appears in B. So we've already done 2 and 3, we just need to add 4 now to the set. So that's the union of A and B. The intersection is quite a simple thing. It is the set of everything that appears in both sets. So 2 and 3 appear in both sets, so the intersection of the sets is just the set of 2 and 3. Now, what if this was not 2, 3, and 4, but 4, 5, and 6? Right? Then the union of the two sets would be 1, 2, 3, 4, 5, and 6. The intersection, however, wouldn't have anything in it, because there's nothing that would appear in A and B if A were 1, 2, 3, and B were 4, 5, 6. Right? The intersection would be empty. And so we have to define a concept of a set that contains nothing. And so let's do that example real quick. So consider the sets A equals the set 1, 2, and 3, and B equals the set 4, 5, and 6, right? The union of them is quite simple. It's just the set of all the numbers from 1 to 6, or all the whole numbers from 1 to 6, right? Pretty easy. But the intersection doesn't contain anything. It is empty. So we can either put two curly brackets with nothing between them, or we use this fancy symbol. It looks like a 0 with a slash through it, a little diagonal slash. And this is called the empty set. It is a perfectly valid object in set theory. It is the set that contains nothing. Keep in mind that this is not equal to this, which is the same thing as writing this. Because this is not the empty set. This is the set that contains the empty set. So there is not nothing in this. The empty set is its own object. It contains nothing, but it is its own thing. So if we put it in a set, then this is a set whose only element is the empty set. And the empty set is an incredibly relevant aspect of set theory because it is essentially, in some ways, sort of like if you were to maybe draw some analogy to like group theory, for example. This is sort of the do-nothing operation in a very vague sense. I'm not trying to associate those things with like rigor, but it's in some way just as useful, just as welcome, just as needed to sort of build a consistent theory is to be able to talk about something that doesn't have anything in it. And so that's going to be an important aspect of when we're talking about sets. When two sets do not contain any of the same elements, we say that they are disjoint. So if the intersection of A and B, some sets, is the empty set, the set that contains nothing, then we say that A and B are disjoint sets. So they contain, they have no adjoining aspects. There's no elements that are common to both sets, and so their intersection is empty. They contain nothing that appears in both sets. The next thing that we're going to talk about is subsets and supersets. They're pretty easy to conceptualize. So a subset of another set is something that contains some or all of the elements of that set. For example, if A is the set 1, 2, and 3, then there are subsets of A that we can consider. So consider big A1 to be the set of just the number 1. This is a subset of A because 1 appears in A. And so the notation that we're going to use is this right here. So a sideways U, meaning that this is a set that can be expressed, that can be found inside, this is a set of elements that can be found inside A. We may also use this symbol, like that, with a little thing at the bottom, a little horizontal bar, which is analogous to things being less than or equal to. So without it, it's called a proper subset, in that it definitely contains not every element of the larger set, right? So this only has the number 1 in it, but we could say that the number A, or the set A, is a subset of itself, right? It contains all the elements. It's not a proper subset because it contains everything that is in A because it is A, but it is a subset in some sense, right? It is something that can be found within A. A can be found within itself, in the sense that all of the elements of A are found in A, which is sort of you could call that a tautology, but it's necessary for the theory. We also say that the empty set is a subset of A. Again, a proper subset because it doesn't contain any of the elements of A. We can take nothing from A, just like we can take everything from A. So if you're going to be able to take everything from A and call that a subset, you should be able to take nothing from A and call that a subset. Which brings us to another topic in sets, which is called the complement of a set. Say we're talking about the set of English letters. So there are 26 letters. We'll call A the set of all the vowels. So little e, little I, little o, and little u. We'll call this V. So V is the set of vowels inside the alphabet, and A is the set of all the letters, lowercase letters from A to Z, or Z as you might call it. So we see that V is definitely a proper subset of A, right? It contains some of the elements of A, but it's not all of them. In fact, it's only 5 out of 26. The point that I want to draw here is that we can talk about everything other than the elements in V, and we call that the complement, or V complement. So V complement, which can be read as V complement or the complement of V, is simply all of the elements of A that do not appear in V. So that's going to be B and C and D. Skipping E, we get to F, and then ... all the way down to X, Y, Z, right? So this will be the 21 letters that are not vowels. So they appear in this set, and that's the complement of a set. And so that's going to be an important thing that we're going to need for our next topic, which is De Morgan's laws. So what we're going to discuss, using complements, intersections, and unions, we're going to talk about De Morgan's laws. And here, I'm going to quickly prove them visually. I'm not going to prove them using set theory in the rigorous sense, using the symbology and things like that. But we will prove them eventually when we solve certain problems. But let's just quickly cover what De Morgan's laws are. So real quick, let's just state what they are. So De Morgan's laws state there's two laws. There's one that states that the complement of A intersected with the complement of B is precisely the complement of the union of A and B. And the complement of A union the complement of B is equal to the complement of the intersection, which is quite a nice thing. So let's prove these two laws with visuals. So let's draw a box that represents the set of everything. So in the context of real analysis, this will pretty much always be the real numbers, all of the numbers on the number line, which we now know are not all rational numbers, by the way, but we're going to start to talk about all of that rigorously in the next few videos. So let's just consider if this is the set A and this is the set B. They may or may not have elements. They could be empty, but the point is that these rules don't reference whether or not they could be empty. So let's talk about the complement of A. That's going to be everything that's not in A. So that's going to be all the stuff outside the circle of A, which means anything that's in B but not in A. All of this stuff is the complement of A. Right? Just like that. And then the complement of B is everything that's not in B. So that's going to be all of this stuff out here. Right? Not in B. So all the stuff that's around the circle B. And we want to find the intersection of the complements of these two things. So if we find the intersection, that's going to be the stuff that's only in both of them. Right? Now, the stuff that's only in both of them is where the orange and the black cross stitchings are both there. And so that would be all the stuff that's outside of both circles. So all the stuff out here, right? That's the intersection. Only the stuff that appears in both of them. Which agrees completely with the right side of the equation, because what is A union B? A union B is everything that's inside either circle. So this shape right here. And the complement of that is everything outside of those two circles. So both sides of these equations agree. Now if we look at the union of the complements of A and B, well, the union of the complements of A and B is going to be everything that's not in B and everything that's not in A, which is going to be all the stuff outside B and all the stuff outside A. And all that leaves us is this intersection right here. And this is the intersection of A and B. But of course, this states that the union of the complements of A and B is the complement of the intersection of A and B, which is of course clearly the case, because this little crescent in the middle is the intersection, and we're talking about everything outside of that. So it's the complement of the intersection of A and B. And so that proves these two theorems visually. It's probably a little bit more fruitful in the context of real analysis to prove these things using set theoretic notation and things like that, just to get used to the method of proof. But this visualization is perfectly valid and rigorous. And so that more or less covers what we're going going to need to know for sets for the meantime. Actually, no, there's one more thing that we need to talk about, and because we're usually pretty much always going to be talking about sets of real numbers, I'm more or less going to be assuming that from here on out, right? If I say A is a set of things, it's going to be a set of real numbers, because essentially that's what we're only going to be studying, which tells us no complex numbers, right? We're not taking the square roots of any negative numbers in this entire series of videos. So let's quickly talk about the potential for infinite unions or infinite intersections. So let's take a particular example. So let's define A1 to be the set of, well, let's just make it equal to the natural numbers. So it's the set of everything from 1, 2, 3, ... all the way up forever and ever. We'll define A2 to be the set of 2 and 3 and 4, ... forever. And in general, we will define A sub n to be the set of all integers starting at n and everything above that. So n, n plus 1, n plus 2, forever and ever. And let's take the intersections of these things. So let's say A1 intersect A2. So this is going to be everything that appears in A1 and A2. Well, that's just everything from 2 and above, because 1 does not appear in A2, but everything from 2 and above does appear in A1 and A2. So this is not empty, right? It contains everything from 2 and above. If we then require that we also intersect it with A3, right? This order doesn't matter, by the way. It's just asking, we're only taking the elements that are in all of these. This is also not empty, right? Because 1 doesn't appear in A2, and 2 doesn't appear in A3, but 3 and above appears in all the sets, right? And in fact, we can continue this up and up and up using this notation here. So we have the intersection from k equals 1 to n of ak. This is going to be a1 intersect a2, intersect a3, blah, 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 all the way up to intersect an. And we will see that this is not empty because the numbers n and above appear in all the sets. So again, this is not empty because it equals the set an, right? It equals an because the intersection of all these things, it contains the numbers from n and above. But if we were to allow this to continue forever and ever, and have what's called an infinite intersection, sort of like the same notation that we would use for sigmas or pi's for products and sums, or integrals or things like that. Things we haven't actually proven to are valid things to do yet, so let's not talk about those yet. But this notation just means that we're taking all the sets A1 as high as we want, up to infinity, and intersecting all of them. Then this is definitely empty. Because there is no set in all of these sets that contains an element from all the sets. Because each time we're cutting off the smallest one, which means that that element no longer appears in any sets after that, right? Once we've gone to A3, none of the sets contain the number 2. Once we've gotten to AM, none of the sets contain the number m minus 1, right? After that point. And so the intersection of all of the sets is empty because none of them contain a number that appears in all of them, right? And so that's the idea of infinite intersections. They can be empty. All of the finite intersections are not empty. In fact, they're infinitely large because it's every number from n whatever to wherever to infinity. But and the same idea can hold for unions, right? There can be infinite unions and et cetera, et cetera. It's not that hard to see how the notation would generalize to those topics. But that's more or less everything that we needed to quickly cover about sets. Everything else will sort of fall into place as we learn the subject more. So in the quick discussion that we did about infinite intersections, I forgot to talk about infinite unions, of course. So let's go back to our definitions that we had before. So we had the set A1, which was equal to the natural numbers. And we quite easily showed that any intersection of these will be non-empty. But the infinite intersection of all of them is empty because no set contains an element that's in every other set, as we keep removing the lowest one for each iteration. And this theoretically goes forever. But we didn't mention unions, right? So clearly A2 is a subset of A1 because it contains everything that A1 has except the element 1. So we have that A1 is a superset of A2, or that A2 is a subset of A1. Also A3 is a subset of that, and if we continue this forever, then that goes in all directions, and every successive set is a subset of the one that came before it. But because each set actually has, is bereft of the lowest element of the set before it, if we were to take the union of any of these, you end up with A1 as the union, because the union of A1 and A2 is just everything that's in A1 put in a set with everything that's in A2. But everything that's in A2 is in A1 because A2 is a set of A1. So this is just A1 again, right? And no matter how many we unionize, you could say, this will always be A1 because A1 has all the elements that all the other sets have. So any finite union of these sets will be equal to A1. In fact, any infinite union of these sets will be, I guess we could use n. It's not a big deal. We could also write this as the union for n in the natural numbers of an. Right? Those are two perfectly valid things. Or you could do A1, union A2, union A3, union A4, all the way up to forever. This is also A1, because at every step we're talking about combining on a set with elements that we've already captured, right? Because everything in all of the AKs is in A1, right? So the union of all of them just gives us that. So sort of like how the finite intersection of these always gave us AN, the finite union and the infinite union of any of these always gives us A1. So this is sort of introducing the idea of infinite unions, and I just wanted to get that across before we continued. What I wanted to quickly do was cover functions real quick as a concept in real analysis, not as a geometric or algebraic representation, but to talk about functions in a very, very general sense. So in a very, very broad meaning, a function is something that acts on two sets. So if we have sets A and B, so these will be, of course, sets of the real numbers. They could be the real numbers, I don't know, but they are sets of the real subsets of the real numbers, as will just about every set in this topic. Or they could be sets of real numbers, but essentially it's going to be constructed from real numbers. That's the idea. And a function from A to B, written like so, is essentially saying we take an element x in A and associate with it, in some sense, associate with some y contained in the set B, right? And this association is given by some rule. And this rule could be arbitrary. I mean, you could just say, take a random element from B and associate, take a random element from A and associate it with randomly to an element from B, and that would technically be a function. Generally we're going to be speaking about rules that are nice, like doubling the element from A and getting the number from B, or squaring it and adding 1, things like that. We will eventually talk about functions as we familiarly know them, as algebraic expressions that could be associated with a geometric picture, if in the Cartesian context. But in reality, a function is this very general idea that we're taking some element from A and mapping it onto some element from B based on some rule that will apply to not necessarily all the elements of A and not necessarily all the elements of B, but we have to talk about those different aspects. So we have to mention injection and surjection. So we say that a function is a function from A to B is 1 to 1. 1 to 1. So we say literally 1 to 1, or more abbreviated as 1-1, or injective. If f of A equals f of B implies that A equals B for some little a and little b contained in the set big A. And f of A and f of B are contained in the set big B, right? Because they are the function, they are the rule, right? We're taking some element of big A, applying a function to it, this rule, and getting some element of big B. So f of A, f of little a, and f of little b are elements of big B, whereas little a and little b are elements of big A. So let's analyze what this means. This is saying a function is what we call 1 to 1 if the output of two elements is the same, means that the original elements were the same to begin with. So, for example, the function f of x equals x squared is not 1 to 1, because we could plug in 2 for A and -2 for B, and we will get 4, despite the fact that a and little b were different numbers. So that would not imply that A and B are equal. All the elements of B that they hit it only once, right? There's no two elements of A that map to the same element of B. That's essentially what injection is. And we would say that a function from A to B is onto or surjective if for all, this upside down A means for all, by the way, and you'll find that a backwards E means there exists. So is onto or surjective if for all y contained in the set B, we have if for all y contained in the set B there exists some little a, or I'll say little x contained in the set A, such that f of x equals y. So these are two distinct concepts. This one is saying that for every element of A, it is mapped onto a unique element of B. And this is saying that for every element of B, there is some element of A that maps onto it. So to give a little visual, the injective part is sort of like this. So say we have a set like 1, 2, 3 for A, right? And a set B, 4, 5, 6, right? This is saying that every 4, 5, 6, 7, we'll say. The injective part is saying that every element of A is mapped to an element of B uniquely, right? There is, each element of A only maps to one element of B, and, it's not the case that more than one element maps to the same element of B. But notice not every element of B is hit by this definition, right? The number 6 does not get mapped onto by whatever function this is, right? It doesn't really matter what it is, just to get across the idea. So this would be called an injection. A surjection is similar in the sense that every element of B is hit. So this could be this, for example, right? We could have 3 elements that 1 maps onto and 1 element that 3 maps onto, but notice that this perfectly well fits the definition of a surjection, right? So every element of B is hit by some element of A. It says nothing about every element of A hitting some element of B. Combining these two things together, we get what's called a bijection, which is a very useful concept. A bijection, so a function from A to B, usually written with like 2 arrows, is bijective if it is both injective and surjective, so one-to-one and onto, which is to say that each element of A maps onto a unique element of B, and every element of B is hit. So a bijection would be something like this. Right, this is a bijection because every element of A uniquely maps onto an element of B, and every element of B is hit by some element in A. So a lot of functions that you're used to will be bijections, or any odd power of x is a bijection. Any polynomial is not in fact a bijection, but 7x cubed is going to be a bijection. 71x to the 9th is going to be a bijection, right? Any multiple of an odd power of x is itself going to be a bijective function. And so these are important things to review about functions that we needed to talk about, and we will be using these words quite freely as we continue these lessons. So please make sure you understand these definitions and are used to them. We should also mention that the set of all the elements of the input set that do get mapped onto the elements of the output set is called the domain of the function, and the output of the set is called the range of the function. Sometimes called the image. It's the set of all the stuff that gets mapped onto, and then the pre-image is all the stuff that maps onto that stuff. But those words are sort of a bit confusing. We'll just mostly stick with domain and range. The domain is the set of all the inputs of the function, and the range is the set of all the outputs of the function. I hope that's clear. The next thing I wanted to talk about was the absolute value function. This is going to be very, very useful for us when we're trying to make bounds for things. If we want to prove that something is infinitely large or something is finitely large, we can use the absolute value to put upper or lower bounds on certain things. So let's define what the absolute value is. So the absolute value of a real number x is this what's called a piecewise function. So it's defined over 2 separate domains, but you've all heard of this function before. It's simply x if x is greater than or equal to 0, and it is negative x if x is less than 0. Because we're saying that if x is negative, but as in it's less than 0, we're going to multiply that by -1 to get the positive version of it, and that's going to be how we define the absolute value. So that may seem a little bit useless in the real numbers because it seems to just make things positive, except 0, of course. But what it actually is the distance of a number to 0, the size of a number. And that definition allows you to generalize to other dimensions, like the plane, right? You can pick a point on the plane and say the size of that number is just its distance to 0. That would be more like talking about complex numbers, though, so we're just going to stick with the real number line throughout this series, of course. And so there's 2 things about the absolute value that I want to prove. I want to prove that the product of absolute values is equal to the absolute value of the product of those numbers. and I want to prove to you the very, very useful triangle inequality, which simply states that the absolute value of a sum of two numbers is always less than or equal to the sum of the absolute values of those two numbers. So this is in particular called the triangle inequality, right? Many of you will have heard of this, and I'm going to prove both of these now. So the first one, the second one I'm going to prove sort of heuristically, like I did with De Morgan's laws. But the first one is pretty easy to prove. You just have to check every case. So either A and B are both positive, they're both negative, or one of them is positive and one of them is negative, right? A and B are just real numbers here. So let's assume A and B are both positive. Then the absolute value of A and the absolute value of B, well, the absolute value of the numbers, which are positive, are their own numbers. So this is just equal to A times B. But of course, if A and B are both positive and we're multiplying them together, we get another positive number. So the absolute value is the same as that positive number. Check. So assume they're both negative. Well, then the absolute value of A times the absolute value of B is going to give us the negative of those things. So we get negative A times negative B, which of course makes positive numbers because we've assumed that A and B are negative. But of course negative 1 times negative 1 is just 1, so we get A times B again, which is of course equal to the absolute value of the product of A and B. Check.
A negative times a negative equals positive.
Now we're going to assume without loss of generality that A is bigger than 0 and B is less than 0. So it could be the other way around, but it doesn't really matter. And then we have the absolute value of A times the absolute value of B is equal to A, because A is positive, times negative B, right? But B is negative, so negative B is positive, which means this is negative AB. And now this is equal to the absolute value of A times B because negative B is positive, because B is negative, which means this is a positive number. Right? And so because it's a positive number, it must be the absolute value of the product of A and B ignoring signs. And so that must be the result there. So that's good. And now the only other thing we had to check was if at least one of them were 0, right? If one of them is 0, then it's quite easy to see what happens. So without loss of generality, assume A equals 0. It doesn't matter what B is. So the absolute value of A times the absolute value of B. This is the same thing as taking the absolute value of 0 times the absolute value of B. Of course, this is 0 times the absolute value of B, but this is 0. And because anything times 0 is 0, but of course this is the same as the absolute value of A times B, because A is 0, so we get 0 times B. 0 times B is 0, so we get the absolute value of 0, which is 0. And so if at least one of them is 0, then all the product will be 0. And so that's every possible case, and so that proves the first one. The second one I'm going to prove with sort of an illustration. So you could imagine A and B to be vectors in 2D space. Now what's a vector? A vector is a quantity that has direction and magnitude. So it's pointing in a particular way, and it has a certain size. And this will evoke the whole triangle aspect of this inequality. Because imagine we have 3 sides of a triangle, right? And we can think of this side as A, and this side as B. And we can think of this side as A plus B. Not in the sense that their sizes add up to that, but if we took A, and then without changing the direction, imagine B were anywhere else, it doesn't really matter. Without changing the direction of B, we append the tail of B to the tip of A, so you could think of there being arrows here, like vectors. And then there's this vector down here. And A plus B is the sum of these two vectors, so really I should put a little arrow above them to indicate that I'm talking about vector quantities. But you'll notice that if we took the path of A plus B, right, this is a shorter path than if we took the path of A and then the path of B. And what that tells us mathematically is that the length of the path of the sum of the two vectors is shorter than the length of the path of each individual vector, right? The length of A plus B is less than the length of A plus the length of B. There was nothing to stop us from maybe drawing these intersections closer, so this could have been A, and this could have been B. Clearly in this case, the absolute value of A plus the absolute value of B is still more than the absolute value of A plus B, but we could just bring this down to the limit, right? We have A being lying along A plus B, and then B being the rest of that, right? And now A and B literally make up the vector A plus B, which allows us to have the less than or equal to aspect of it. So if the path is longer, the absolute value of A plus B is strictly less than the absolute value of A plus the absolute value of B. Or they could lie directly on that vector and they represent the same amount. And now, That was just sort of a heuristic explanation for why this is true. Of course, the real numbers all lie on the real number line, and of course, so when you're adding, you're only going in those two directions, and so any vector on the line is going to be pointing in those two directions. But essentially, this works for numbers as quantities as well, because the whole idea of going backwards is just a negative value. And so this does work in general. And so that's what I wanted to mention about absolute value for now. Eventually we'll get to something called the reverse triangle inequality, which sort of helps you put, this helps you put upper bounds on things. The reverse triangle inequality helps you put lower bounds on things. Okay, so for the last thing I wanted to talk about in this preliminary video for my series on real analysis is methods of proof. We've exercised contradiction. We proved that the square root of 2 is not a member of the rational numbers, right? By assuming that it was, and then showing that that led to an absurd conclusion, which does not agree with reality. There is direct proof, which is you start with some assumptions and you just follow the path of logic until you reach the conclusion. And we did that by proving that the absolute value of A times the absolute value of B is equal to the absolute value of A times B. That was a direct proof, right? We just considered every possible case and proved it. That was all we had to do. And there's one more, and I'm going to show one more proof that's going to involve both of these, but I'm just going to explain the final one, and this is going to be very, very useful for us in real analysis because we're going to be talking a lot about mapping the natural numbers onto another set of things, and so that's going to require something called induction. So induction is sort of a strange idea. For those of you who haven't heard of it, it's essentially the domino effect, right? If you're able to knock over one domino, and then prove that other dominoes get knocked down, then all the dominoes get knocked down. So for example, so say you had some statement. Some statement x is true for all n in the natural numbers. So x is just some statement. It's like some proposition about the natural numbers. So what you do then is you want to prove that it is true for n equals 1. So n equals 1 is true. It's like the base case, right? It's the simplest case of the claim. And you want to prove that it's true. Then what you want to do is assume that n equals k for some value of k is true. This is called the induction hypothesis. The induction hypothesis is an assumption to be made. So first you have to prove the base case. If you can't prove the base case, it doesn't matter. After that, the induction isn't going to work. Then you have to assume that some value of n works. Just assume it. Make it hold that it is true. Then from this assumption, you want to prove that this implies that the case n equals k plus 1 is true. So you want to, from this assumption, prove that the next case is true. Then the proof is done. Because, so say you had some proposition about the natural numbers, you prove that the base case works. Then, upon assuming that some case works, you are able to show that that means that the next one must work. But we didn't specify what that value of k was. It could be anything. In particular, it could be 1. But if we're able to show that the kth case proves the k plus first case for any k, then we can assume that k is 1, which would imply that n equals 2 works. And then n equals 2 would imply that n equals 3 works, and which implies that n equals 4 works. And it's the domino effect, right? One domino knocks over another. And so essentially what you're doing is you're proving that the first domino falls over. And you're proving that if any domino falls over, it knocks over the next domino, which means that the first domino knocks over the second, which knocks over the third, which knocks over the fourth, and the proof is complete. And so induction is going to be very, very useful when it comes to talking about the input of a function being like the natural numbers and those mapping onto other things. So it's going to be a nice way of relating natural numbers to other sets of things. So induction is going to be very useful, but I want to give you one more example of something that contains both a direct and indirect proof. By the way, contradiction is known as an indirect proof because you're not going directly to the conclusion. You're assuming that the opposite is true and then showing that that assumption can't be the case, which leads you to the conclusion that the original assumption must be true, or the original conjecture must be true. So let's take a look at something that on the face of it seems rather trivial, but actually gives us a tool that we're going to be using an incalculable number of times throughout this series. We're going to prove a theorem that seems a bit trivial, but it is very important to develop this kind of intuition for things. So, given A and B in the real numbers, which is this fancy schmancy symbol here that you saw at the beginning, so this is like all the integers and all the rational numbers, and then any other numbers we're able to have in there. We proved that the square root of 2 was not rational, but we did not prove that it was a real number, so we need to actually prove that at some point. I know I sort of spoke of it as though it was, because we're all so used to it. It's sort of hard to escape the language that we use, but we haven't proven that the square root of 2 is a real number. But let's just take a and b to be any real numbers, which of course can be expressed in their decimal form or binary form or fractions or infinite whatever you want to, it doesn't really matter. They're real numbers. Then a equals b if and only if the absolute value of the difference between a and b is less than some number epsilon for all epsilon greater than 0. So let's observe what this is saying. This is saying that we're taking two real numbers, a and b, and then we're saying that they can only be equal if the difference between them is smaller than any positive number. Now that seems obvious, because if they're equal, the difference between them is 0. And that's actually the first direction of the proof, because what does if and only if mean? If and only if means that this implies this, and this implies this. So it's a bi-conditional statement. Both parts of the theorem can be the hypothesis, and they each imply the other part, which is the conclusion, and we have to prove both directions. So the first direction is a direct proof, if not sort of trivial, right? So we assume a and b are equal, right? Assume a and b are equal. Then the difference between them, absolute value or not, is precisely 0. Since 0 is less than epsilon for all epsilon greater than 0 by definition, we're done, right? So the difference between them is 0 because they are equal, and 0 is less than all positive numbers epsilon, so therefore we're done, right? This implies this. So now we have to assume this and show that it implies that a equals b. So this was the direct proof, and now this one will require proof by contradiction. So assume that the absolute value of the difference between a and b is less than epsilon for all epsilon greater than 0. Now, we can't assume that a equals b because that's what we're trying to prove, but we want to show that there's maybe a logical contradiction here. So let's assume that a is not equal to b, and show that these two assumptions together don't make any sense. But of course, there's nothing individually bad about this assumption or this assumption, but we want to keep this assumption. So because we want to keep this assumption, if both assumptions lead to a contradiction together, then this must be the assumption that's bad, because we want to keep this one. Right? So let's see what this says. So if a does not equal b, then that means the difference between them is not 0, right? A minus b is in particular equal to some delta, which is greater than 0, right? It's some positive number that is the distance between a and b. So now let epsilon equal delta over 2, right? So delta is just some positive number because it's the difference, the absolute value of a difference between two numbers. A minus b, the absolute value of it, is not less than epsilon, which is equal to half of delta. And so we have been able to find an epsilon that is greater than 0, which the difference of a and b is not less than that, right? Which contradicts this assumption. But since we want to keep this assumption, and it's the fact that both of them together lead to the contradiction, it must be that this is the problem. And so it must be the case, therefore, that a does in fact equal b, which proves the other direction, and therefore the theorem is complete. It is true that a and b are equal if and only if the absolute value of their difference is less than any positive number epsilon. And so this kind of thing, this idea here, is going to be ubiquitous throughout this series. And so you should get very, very used to seeing things like this and considering very, very small gaps between things, because the point is that epsilon gets as tiny as we want, right? It gets as close to 0 as we could possibly want, because the whole point is that the difference of between equal numbers is 0. So any positive number will do, no matter how small. In principle, it could be any number, though, right? We didn't care how far away a and b were in this case. We just knew that they were some distance apart, delta. Could be any number. It could be a billion. It could be 1/100000th. It doesn't matter. All we needed to do was see that it was some number that wasn't 0, and that we could make an epsilon smaller than that for which the difference is not less than epsilon, which contradicts the pair of assumptions, which led us to the conclusion that a must in fact equal b. So that's sort of covered every preliminary that I wanted to talk about for this video. It's quite a long video. I'm going to try and keep these under an hour. If they go over an hour, I'll probably split them up into 2, but we'll see how that goes, because this is sort of a lecture series, so an hour really should be just fine. So thank you very much for watching this preliminary episode. of our series on real analysis. In the next video, we will be talking about the axiom of completeness. So, and among a couple other topics. So thank you very much again, and I'll see you in the next video.